Hello everyone, our project topic is single image super resolution generation via GANs. In today's presentation, I'm going to show our projects from the following 5 aspects.
First, about our motivation. We know that the highly challenging task of estimating a high resolution image from its low resolution image is referred to as super resolution. In other words, SR resolution. SR images received substantial attention from within the computer vision research community and has a wide range of applications. About this topic, a traditional method is to minimize the mean squared error, MSE, between the recovered high-resolution image and the ground truth. However, the ability of MSE to capture perceptually relevant differences, such as high texture detail, something like that, is very limited as due to they are defined based on pixel-wise image and differences. So in our project, we use a generative adversarial network to solve this problem, as well as a deep residual convolutional neural network with skip connection. And then we use the latest loss function combined with mean squared error loss and feature loss. Well, let me introduce some information of our dataset. We use BSDS100 dataset. Our algorithm is based on SRGAN, which proposed perceptron loss function. Based on it, we also applied the updated residual network structure and merged some other loss functions as our null point. Now look at the specific structure of our network. First, we can see the architecture of total GANs. This is a flow chart from the beginning. HR images have been put from the datasets. We are downsampling them to get low resolution images. And then we put lower resolution image into the generator network. This network will generate a fake image which has a higher resolution. In other words, it's super resolution images. And then we can push these fake images and the ground truth image into the discriminator network. In the final discriminator network, we can simply consider it as a binary classifier. After we compute the loss between true and fake higher resolution images, we can update the two networks above to get more realistic fake pictures. Next, we are going to turn our attention to the generator network specifically. First, we take LR images as inputs, and then we are upscaling to get a large size picture with low resolution. Then we tend to use residual blocks you can see here with skip connection to do the convolution. That's an important structure in our model. Each block has two convolutional neural network layer and two bench normalization layer. And it's helpful for avoiding stop at local minima during training process. Another thing is about the skip connection. This can prevent vanishing gradient problem because it's achieved the cross-layer propagation of gradient. Okay, let's look at the loss function part. There are three kinds of loss function. First, in order to pick up the texture details and generate it properly, we use a perceptron loss, in other words, feature loss. That is computed by comparing the ground truth and the generated fake pictures in one layer of VGG networks. And second one is the content loss. This function can be simply considered as MSE between high resolution image and super resolution images. And then we combine this one and the perceptron loss function as the loss function of generator network in total. In addition, for the total GANs, we need to add the adversarial loss to complete total loss of whole network structure. This loss ensure that we can improve training of generator if there are high loss of fake images, and that we can improve training of discriminator when the loss of true pictures are higher. Well, next part is implementation. In this part, I'm going to introduce some difficulties and solutions in our projects. First one is about the parameter of loss function. And remember the three loss function above, because the reference paper doesn't give appropriate value for our data set, so that we adjust the various ratio of three loss to get an optimal performance. And then in the upscaling part, we attempt two methods to achieve our goals. And that is using different sequence of convolutional layer and upscaling layer. After several tests, we found its performance better when we do the upscaling first, although it's consumed more time, instead do it later, such as SR GAN paper. Next slide, we add one layer of bench normalization based on SR GAN when we design our residual blocks, which can efficiently avoid gradient variation problem In addition, we also choose a new layer of VGG network to compute the loss. Using the new layer, we can decrease the influence of the MSE loss, and then we can wait to generate more smooth picture and obtain more details in our generated super resolution images.
When we begin training, we monitor the accuracy of the discriminator for every epoch. And at first, we noticed that the accuracy of the discriminator is always 0. And we thought that the discriminator is not so strong, so we could change our training strategy. So in the training process, for the one batch, we do one SGD for one batch. And for the generators, we do 2 SGDs. We believe in this way, the GAN network could perform better. However, we trained in this way for some epochs, and we noticed that the accuracy of the discriminators keeps 1. And this means the generators completely fool the discriminator. We recognize that the discriminators still needs to be trained. So in this way, we keep our old strategy. For each batch, we do 1 SGD for discriminators and 1 for generator. And the next question is the memory limitation. To train the network, just like our homework, 8 or 16 pictures per batch. However, we encounter the error that we cannot allocate the memory for training. We at first simplify our network, like reduce the number of ResNet blocks, but we still cannot resolve the problem. Then we reduce the batch size, and at last, we reduce the batch size to 2 and do the training successfully. And here is the result of our work. The left pictures are from a traditional interpolation method, biologic interpolation, and the second and the third are from the training results. The second is a result we train with the MSE loss function, and the second is we train with perceptual loss. And in this way, we can say it's very close to the ground truth. The ground truth is a force in our screen. And for the second one, the MSE loss function, we think is a little bit overfitting, and our data set do not have too much pictures, and the color of the have changed a little. And for the loss function, we found that if we zoom the pictures, and we can find that with VGG loss, the algorithm could recover the texture of the picture better than MSE. Sometimes the result of MSE is smoother than VGG loss. And here is the bad results. We can find that the surface of the crocodile and the stone on the ground is not recovered very well. And then we compute some numerical criteria of our result. First is the PSNR, which is used to compute the ratio between the peak signal and the noise between the generated picture and the ground truth picture. And then it's SSIM, is the structure similarity between the generated pictures and the ground truth pictures. From these numbers, we can notice that the loss functions with perceptual loss better than MSE and better than biologic interpolation. Then we want to talk about our future work. First, we want to use our algorithm on a larger dataset. Second, we want to spend more time on fine-tuning the hyperparameters of our network because we only train for around 500 epochs, and we want our PSNR and SSM perform better. And third, we also read some papers for supervised learning super resolutions for recent years, and we noticed that the structure of the neural network is almost fixed. So we want to explore better loss functions to make the network perform better. That's all of our presentation. Thank you for listening.